So here the next topic is 9.5 generators and relations. In abstract algebra, of which the theory of abelian groups form a small but important part, the most important features are the underlying patterns, but the elements, we don't recommend our elements, but we are concerned with the underlying patterns. So the one abstract way to define abelian groups is to provide a group table which we can use this to find the sum of any two elements without having to be bothered what the elements really are. But this is clearly no good for the infinite curves. So here we will use generators and relation space. As we can see on the screen, uh, uh, the another way to define abelian terms abstractly is to use generators and relations. So it's simply a linear combination like this. If we have two variables, two numbers, so we can add simply to each other, and we the linear combination we can write it as by simply this way, and next we can take our integers separately. And this, since this is an abelian group, so the identity its closure under addition, it's obvious because it's a linear combination, and the identity of this formal linear combination is this, and the inverse of the formal linear combination is this. So it's simply a abelian group, and we can denote the group of all formal linear combinations like this by using our square brackets. So here we do the next example. So for this regarding, we'll do example related to the relation. And these are the two generators which are involved with the one relation. So in this group, the sum of these, any two coefficients belong to the integers, we can write it as, and we can simply add these integers, and we get our new relation, which is like 8x plus negative 5 of y. You can see there are lots of equations of linear combinations, which is equal, we put these equations to 0. Here we can make more generators and more copies of our modulus z, which is interesting in doing. As a consequence of these relations, we have to identify many of the formal linear equations in a group to one another. So in this regarding, we do the next example. The concept should be clear by doing the next example. Here I have the example on the screen in which I have two generators and one relation. We can write it the other relation like this, and we simply add the previous relation on it, and we'll get 10x plus 15y. From here, we can't conclude that this is similar to 2x plus 3y. Why? Because in relations and generator, addition and subtractions are possible, but not division, because for this relation, our constants are belongs to integers. And if we'll divide, we can get 1.5 by dividing this. So which is a rational, which can be a rational number or rational which isn't an integer. From the above equation, we have seen 3x plus 5 equals 0. We can conclude that it can be written as like this. So here 3x is a linear combination of the multiples of y. This means that the elements of a abelian group can be split into three disjoint subsets like this, as you can see on the screen, where it's n through ny, n belongs to the integers, and we can add simply the other number and the choice of the other number where our integers belong to the numbers belong to the integers. If we have such a set relations, R1 equals R2 equals till mth term, we can denote our abelian group that's generated by these variables subject to these relations by this. We can simply write it in this form, our generators or relations. So in this regarding, we do the example, which is considers x such that 7x equals 0. A formal linear combination of one generator is simply a formal multiple. So the elements of this group have to form an x plus 4, where are the coefficient belongs to the integers, but because of the relation 7x equals 0, the distinct element can be 0x, 2x, 3x, 4x, 5x, sorry, not y, and 6x. If, for example, if we add two numbers from our distinct elements, so we'll get 9x. So in this, it is clear that this group is simply the group of integers mod 7. So we can write it in the form of isomorphism. X is that 7x equal, it is isomorphic to the mod of Z7, right? I have the another question, which is isomorphic to mod of Z3 with direct sum of mod of Z5. The relation can be written as like this, as you can see on your screen. Uh, Here it is 3x. We can write it till 2x because we are concerning with mod of Z3. And here we can generate a relation till 4y because we are concerning with our mod of Z5. So 0y, 2y, 3y, 4y. Here we are taking our x0. And the next in here it is x plus y, x plus twice of y, x plus thrice of y, it's a fourth of y. And next, here we'll stop because we are concerning with z of phi, mod z of phi. Next is twice of x plus y, twice of x plus twice of y, twice of x plus thrice of y, and next is twice of x plus 4y. And the isomorphic function, we can write it as like this. So it is isomorphic to the model Z3 with their direct sum of model Z5. So simply the relations in generator, if we have a given a relation, we can generate more relations. And if the generators are given, we can find our relations. It's for infinite groups. Okay.